Thanks for coming out so early in the morning. I'm David. I come from Singapore. If you do not know where Singapore is, I think the most important thing to remember is the time difference, exactly 12 hours. So it's about as bad as it can be, cannot be worse. So my main objective is to finish before the jet lag hits me at full force. Right, so you're so I'm going to talk about motion planning, and so let's start with two examples. So one is we have this self-driving vehicle driving on our university's campus plaza with many pedestrians around, right? So if we think about if we want to get a vehicle drive like that, we have to deal with a number of important issues. Obstacles, as we must be collision-free. We have trees and lantern poles, all sorts of things. And the vehicle must respect its own dynamics. It cannot stop instantaneously if it is driving at a high speed. And also that we have environment that changes dynamically because we have these pedestrians moving around. And furthermore, the vehicle control is not perfect and the sensors are noisy. While we think that the robot sees something like this, but it's actually not true. What the vehicle really sees is something like this, right? It's very noisy, even if we have a laser scanner. Now, let me give you then a different example of motion planning. This one. So we have a multi-linked manipulator arm with, in fact, 35 degrees of freedom. It is trying to manipulate itself to achieve a certain pose. Now, clearly that this one is a simulation environment, so at least in theory, we can control and simulate the robot perfectly. There's no noise, and we can know the exact state of the robot as well, and the environment is static. So the only complication is this geometric obstructions as well as many degrees of freedom. It turns out, even without uncertainty, without changing environment, this in itself is hard enough. Okay? So although these two examples looks kind of different visually, we can nevertheless formulate a single motion planning problem. Right? So the problem is to find the optimal or near optimal motion that satisfies all the constraints for a robot to move from an initial state to a goal state. Right? So what the kind of constraints we can deal with, so it has to be collision-free, avoid all the obstacles. We have kinematics, we have dynamics, right? And also that we want motion to be optimal in terms of shortest distance, minimum amount of time, and the motion should be smooth and so on and so forth. Right? Now, it's unfortunately, the many variants of this motion planning problem are proven to be computationally intractable in the worst case. Right? So I'm using this word intractable in a technical sense, that it's NP hard, P space hard, and so on and so forth. And if you're not familiar with this kind of results, it may be a little bit counterintuitive why this problem will be so hard, right? So if you've never been to the Status Center before, the first day you come here, you just solve the motion planning problem to come here, right? So if you extend your hand at this moment in time to grab an object, surely you will reach the object, no problem. So why the problem is so hard? Doesn't seem to be so intuitively, right? So the key word here is intractable in the worst case. In fact, that there is a way to reconcile our intuition and the theoretical result, and I'll get to that a bit later, right? Now, we have a really many variety of different kind of robots. We have those robots on the ground, in the air, under the sea. We have robots that are round, rectangular, and so on and so forth. We have robots that has a rigid body like this, but we also have robots that the manipulator arm consists of many rigid pieces linked together and moving in an articulated manner, right? And these are the 2D abstract version of those things on the top. Given the wider variety of different kind of robots we have, one question we must ask, what is the solution form we seek? Do we want a specific motion planning algorithm for each kind of robot, or we want a general algorithm for all robots altogether? Right? So this is one question we want to ask. So I would like to advocate for a general algorithm. One reason is that by abstract away the details, specific details of robots and come up with a general solution, we will be able to zoom in on the core difficulty of motion planning. Right? And there are also many other benefits as well. Now, one surprising thing is that we are actually will be able to do this at all, right? Given all the variety of different kind of robots with different shapes, with different kind of constraints on their motion, we can actually formulate the problem and solve it with a single algorithm. And for that, we need to define the notion of configuration. It's a simple but a very powerful idea. The configuration of a moving object or robot is simply a set of parameters that completely specifies the position of every point on the object, or on the robot, right? Now, think of that as a point in a high-dimensional space. So the configuration space simply is a set of all possible configurations, right? And that configuration is a point in this parameter space. Okay? So for example, if you have a disk robot, I can choose the center of a disk as a reference point and specify the position of this reference point. And that alone determines the position of every other points on the disk. Now, there are a few things that are important that are associated with the configuration space or the C space. One important thing is the configuration of this, the dimension of this space. The dimension of the C space is a minimum number of parameters required to specify the configuration. Right? So the key word here is minimum. There are different ways to parameterize the configuration, but we want the minimum parameterization, the minimum parameters. And that is an inherent property of the robot motion. And it does not, it's independent of the particular parameterization we use, right? So it's the minimum for. Now, some concrete examples. For example, we have a rigid body robot translating and rotating in a 2D environment. So how do we specify its configuration? We take a reference point and specify its position, X and Y, and we specify the orientation of this object with respect to the horizontal axis, right? So X, Y, theta, right? That specifies the configuration of a rigid body translating, rotating in 2D. We can parameterize this differently. So this is a 4-parameter parameterization. The position is again still X and Y, but we would represent rotation differently using a unit vector U and V. In particular, U could be cosine theta and V equal to sine theta, and theta is the orientation of the object. Right? So that does not change the dimension of the space, right? It just changes the parameterization. And there are various reasons why we want to use different parameterizations. Now, another thing that's important is to keep in mind is we have to have some notion of the shape of this configuration space, right? So the shape of this space is actually a 3D cylinder because the position is a 2-dimensional space, right? X and Y. And we take cross product with a circle because orientation is a circle. Right? So it's a cross product of an R2 and S1. Right? So this is a 2D situation. And if we have a rigid body in 3D, we just need to extend it a little bit. So we still have position, but that's X, Y, and Z. And then we have to specify the rotation. In 3D, we have a variety of different ways to parameterize the rotation space. You can use orthonormal matrices, you can use Euler angles, and you can use more sophisticated quaternion representations. Right? So the details aside, so orthonormal matrices, you would have 9 parameters, but you have 6 constraints because you have each of the unit vector, right? So 3 of them, and they all have be orthogonal to 3 pairs. So 6 constraints, 9 minus 6. There's 3 degrees of freedom, so it's a 3-dimensional space. And if you use Euler angles, you would know exactly 3 parameters, right? And the unit quaternion, the 4 parameters, but you have a constraint, it's be a unit, so it's again 3-dimensional space, right? So now, what if I have an articulated robot, right, with many rigid pieces? Suppose that we parameterize the articulated robots using the joint angles, and I have n different joint angles, then I would have n-dimensional configuration space, and it's a cross product of a bunch of circles. Right? So, now, obstacles. Now, a configuration is collision-free or free if we set the robot at that configuration, the robot does not collide with any of the obstacles in the space, right? And then the set of all free configurations forms a free space. and the set of configurations that leads to collision of the robot with obstacles. We call that configuration space obstacles, or C obstacles. Sometimes the robot does not collide, an articulated robot may not collide with external obstacles, but it collides with itself, right? So self-collision, that's also considered to be C obstacle as well. Now, I want to show you a concrete picture of what C obstacles looks like. So on the left is a workspace, or the physical space that the robots reside in. What I have is these shaded areas are the obstacles, the physical obstacles. This is a two-dimensional workspace. And my robot is a two-link articulated robots that are fixed at the base here. Okay? So I'm drawing two different poses of the robot. Okay? One orange and the other one is kind of bluish over here. Okay? Now, you wonder in the configuration space what all these things will look like. That's shown on the right. Right? So the configuration space, I said that it's a set of all configurations, which means the set of all joint angles. This is a 2 degrees of freedom, two-link robot, so I have two joint angles. This is the first joint angle, the one that's closer to the base, and this is the second joint angle. Each of them goes from 0 to 2 pi. Okay? Now, every pose of this physical robots corresponds to some particular configuration setting, right? So I have this blue one over here, which is represented by this point, and this orange one over here represented by this point over here. Okay. Now I said that the set of all configurations that leads to collision of a robot with obstacle is called configuration obstacles, right? So this is a set of all configurations that leads to collision of the robot with obstacles. And now, roughly speaking, this piece over here, when the robot configuration collides with this piece, it gets mapped to this piece over here. Right? So geometrically, well, these two spaces look very different, right? And in fact, the dimensionality of this space could be different. In this case, this is a two-dimensional, this is also two-dimensional. That's a coincidence, right? So if I have a three-linked robot and this here space over here will be three-dimensional. If I have an n-linked robot, here it will be n-dimensional configuration space. And the shape of those configuration space can be very strange or very complex. Okay? Now, yeah. Joint space, that's correct, yes. Yeah, that's another name. So there are a few names in the literature. They roughly mean the same thing, the joint space, the configuration space, and you can also call that state space as well. It's a matter of definition. Yeah. Now, we can endow the configuration space with a metric, and that turns out to be an important thing. Any mathematically valid metric can be used. For example, we can use a Euclidean distance, except that, of course, we want the metric to capture certain properties of the motion, right? So Euclidean space may or may not be the best possible in terms of for doing that. And here's an alternative, which is consider robot A with some geometric shape. So the metric I want to use is if I want to move a robot from one configuration to the other configuration, I'm looking at all the points on the robot and how much it has moved. And I'll define the metric as a distance that for the point that has moved the maximum amount. Right? That turns out to be a metric and satisfy all the usual properties of a metric. Okay? And to calculate that, well, I mean, since I have to take a maximization of all the possible points, and you may wonder how I actually compute it, because there's a continuous set of points. And for some robots, you can calculate that. In particular, if it's a rigid body with a compact set, geometric set, you can do that. And you just need to figure out the points that is the greatest distance from the reference point. Okay? So, I mean, the details I put on the slide, but that's probably not the most important thing for understanding. Well, the most important thing in the configuration space is a path, right? So the path a continuous path that goes from an initial configuration to a goal configuration. And along the way, that specifies all the configurations that the robot is going to go through, right? So that actually specifies the motion. So what it will look like is something like this. Suppose that this is the initial configuration, and this is the final configuration. And there's a sequence of motion that takes the robot from the initial configuration to the goal configuration without colliding with any kind of obstacles. And you can imagine that roughly the robot has to fold itself and then extend it back out, right? So that in the configuration space corresponds to something like this, right? So a little bit of intuition, right? So you can see that initially, let me see, initially this orange point is here. So you can see that the robot cannot move too much, right? Because if you move any of the angle too much, you will collide over here or collide over here. Change any of the two joint angles, you may collide, right? So that's why it's very constrained over here. Okay. Now, once the robot folds up, you can see that in this middle portion, the space is relatively free. You can change the base angle, I mean, like this piece over here, right? And once you extend itself, it gets into here, it again becomes very constrained. You cannot change the first angle or the second angle because either way you go like horizontally or go vertically, either way you cause your collision, right? So one of the nice thing here is that here we have to think of all the details of the motion, how the shapes of the robot changes. In the configuration space, it's just a curve, a path, right? Now we can specify all sorts of properties we want for this kind of path. I want it to be bounded to curvature because my car has a minimum turning radius, or I want to have certain constraints, holonomic constraints, non-holonomic constraints. For example, we want to ensure that a car cannot move sideways, otherwise that motion is not valid, right? So one of the nice things here is that now we can abstract all the information about motion planning, regardless of a specific geometric shape, the motion constraint of the robot gets all compactly captured abstractly in the configuration space. In the configuration space, at least mentally, all we need to think about is a path for a point, right? So doesn't matter what kind of robot we start with. I mean, it's a rigid body, it's articulated, it's a car, it's a flying drone or underwater vehicle. It becomes a point in the configuration space, except that this point must sit in the right kind of space, and we have to specify the constraints on the kind of path properties we have on the kind of path I want. Okay. Of course, being able to formulate the problem nicely does not automatically solve it, but it helps us to understand, at least help us to say what the difficulty actually is. Okay? So we know that I kind of claimed at the beginning that the motion planning problem is kind of very difficult. And one way to understand this difficulty is to think about the dimensionality of the configuration space. Okay? So here's a concrete example here. It's a rigid body. There are two rigid bodies, a blue one and the orange one. I mean, it's a nail puzzle. How many of you played with those nail puzzles that you have to separate these two nails? You play with that, right? It's hard, right? It at least takes a while. Even if somebody just shows you, normally I would bring a pair, sorry, I'm traveling, so I forgot. So even somebody shows you, right? And after you repeat it, even that is not exactly simple either, right? So, this is a motion planning problem with some initial configuration, and the goal configuration have two pieces separated, and you want to separate them, right? So this is a 6-dimensional configuration space, right? And in order to achieve the final configuration, you have to go through a very specific sequence of motions and go through a particular place, right? You have to maneuver in a particular way. That means there's some place in the configuration space that you must go through, right? You have to go through there. There's very little leeway over there. So if you think about a high-dimensional space, there is a specific point in that space you must go through. You have to identify that place. So that's a search problem. In particular, search for a needle in a haystack. The bigger the space, the harder it becomes, right? So how does the space become big? If I have many degrees of freedom, in this case, it's just a 6, but you can imagine my robots have multiple robots. I have robots with many degrees of freedom. Think about that insertion task I showed that for the 35 degrees of freedom articulated robots to achieve a particular configuration, right? So our difficulty now, at least one major difficulty for motion planning, is just about a high-dimensional configuration space and search for a needle in a haystack. Just that. Okay? So how do we find a path if that is the case? And in fact, it turns out that motion planning devoted at least an entire decade or more. So the configuration space motion planning approach showed up at the end of 70s and early 80s, and for more than 10 years until the mid-90s, the entire effort is just to solve this problem. Find a path in a high-dimensional configuration space, right? And the answer turned out to be surprisingly simple. Okay, so this is my configuration space. I'm drawing it in this weird way because imagine there's a high-dimensional space and all the obstacles have those weird shapes that we cannot explicitly represent, right? So these red pieces, yes. High-dimensional spaces, there are many myriad of paths over there, and if you think about the example that I gave, I have to go through a specific place. So a priori, I wouldn't know which path it is, and I have to explore, in the worst case, the entire space. And this entire space, a high-dimensional space, will have many, many configurations and states, and therefore that it's just state-space explosion, or you can also call it the curse of dimensionality. So this is my high-dimensional space, configuration space. These red things are obstacles. And this idea for solving this problem seems to be almost surprisingly simple. So I said the idea is, okay, let me sample. Okay, so I'll toss a bunch of randomly generated configurations into the configuration space, and I retain all the free ones. If I happen to toss one into a collision C obstacle, I just throw it away. Never mind. I just keep all the ones that are free. Okay. Now, for all the pairs of free configurations, I'm going to check whether it's a simple path that connects them together. Okay. And therefore, I managed to form this graph, which I'm going to call the roadmap. Now, suppose I want to figure out how to go from here to over here. The first thing is that I'm trying to connect this start configuration to some node in the roadmap, and similarly, I'm also going to connect the goal node to the roadmap, and then I'm going to search this graph. I already have a roadmap graph. I can apply a standard search algorithm to search the graph for a path, and that's it. All right. So this is the idea, and so slightly more formally, I'm going to define a probabilistic roadmap as a graph. The nodes of this graph are randomly sampled collision-free configurations, and there's an edge between two nodes of this graph if there's a simple path that's collision-free between these two configurations. Simple could be defined in a suitable way depending on your task. Usually we just take a straight line path between them. Okay. Right. So this is the algorithm in pseudocode. I'm not expecting you to read it, but the two important things here is two primitives. I mean, this is really, if you think about what I just said, it's a very, very simple algorithm. You just say about tossing some samples, right? So I have to determine that the samples are collision-free or not. I need to have a geometric primitive that supports this operation. And also, I need to be able to confirm that there's a straight line path between two configurations. I really need these two primitives. And in fact, I can write this primitive in terms of this one as well. And so if I want to know the straight line path between two configurations is collision-free, I can discretize it up to a certain resolution and check each of these discretized configurations along the path are collision-free. If so, I'm going to regard this collision as this path as collision-free. So this determines the collision-free up to a certain fixed resolution, but in fact there are slightly clever things you can do if I do distance computation instead of collision detection at a particular configuration only, and then I'll be able to, in fact, really confirm that this entire path at the continuous level is collision-free. Right? So these are just some details. Let's assume that these primitives are available to us. Now, once we have that, so we have a graph, and I'm just going to search the graph, okay, and for a path. right? And this is one search algorithm. So I'm searching for a path in the graph. I'm not trying to insult your intelligence by writing down the Dijkstra's algorithm for the shortest path search here. But my main point here is that I need a graph search algorithm. You could use this one, or you could use any other ones, the depth first search, breadth first search, best first, any other favorite search algorithm. And I've chosen here, this algorithm here, actually for a specific reason that I'm going to be useful to us later on when we talk about optimal planning. Okay, so now one question I want to ask you, however, is that I said that suppose I use Dijkstra's algorithm to search for the shortest path in a graph, right? Suppose I find this path. Is this path optimal for our motion planning problem? No. Yeah. Why? Oh, this is computational efficiency. I'm just talking about correctness here. Okay, so yeah. Huh? Oh, but the Dijkstra's algorithm giving me a shortest path in the graph, right? Because of the graph, right? So I'm searching for the shortest path in the graph, but the graph may not contain the real shortest path in the first place, right? So that is a real problem. Okay. Now, this almost sounds too good to be true, right? This idea is so simple. In the beginning, I said it's computationally intractable, and then come up with this algorithm. So does it work? I mean, if so, why? And does it always work? Right? So for that, let's first have to say what does it mean? It works, right? So suppose my algorithm return me a path and say, well, this is the answer. Well, assuming my primitives are correctly implemented, that is indeed a collision-free path. Right? There's no doubt about that. Now, if the algorithm tells me, no, I couldn't find a path, how about that one? Well, that one may or may not be correct, the answer of no path. It could be because there's indeed no path. If there's no path, you would not be able to find one. But also it could be that there is a path. It's just difficult to find. The algorithm does not find it, for example, because I haven't sampled enough, right? So this space here is connected, right? So the red parts are the obstacles. The underlying free space is connected, so you can go anywhere to anywhere. Except if you look at my roadmap graph, it has 3 connected components, right? So it does not fully capture the underlying connectivity of the space. So if it tells me that there's no path, the answer may or may not be correct. So it may make mistakes, one-sided mistakes. Right? So the algorithm that I just told you about is in fact not complete. Right? So now suppose that I end up with a roadmap like this, and well, it's not complete, right? In the sense of planning, the planning algorithm is not complete. It doesn't always give me the correct answer. What can I do about that? Huh? Add some more samples. Okay, good. Add some more samples. Yeah, you want some?
You could do your sampling towards the edges and towards the nose. Yeah. You could bias your sampling towards the edges.
That's right. I think that could be another reason why I fail to find correctness. Right. So if we want to add more samples in order to improve the algorithm, then, well, even if I add sometimes because exactly like what's suggested here, because of bias, even I add an infinite number of samples, I may still not be able to find the correct answer because I'm all adding samples in the wrong place, right? So even if I can add infinite number of samples, I still need a notion in which that says that if I add enough samples, that I will be able to solve the problem correctly. So that's called probabilistic completeness, right? So probabilistic completeness that says if no solution actually exists, then the algorithm must tell me that no, there's no path. Okay. Now, if a solution actually exists, then my algorithm is supposed to find it and guarantee to find it with high probability. Right? So this is make sure that the distribution for sampling actually is good. So well, our algorithm the very simple algorithm we start with, it just use uniform sampling, right? I mean, uniformly sample the configuration space. That turns out to be probabilistic complete. It may not be not the best possible, but actually it is probabilistically complete, and we can prove it. If there is a path, the algorithm will find it with high probability after sufficient number of samples have been taken. Right? So I want to very briefly tell you how would we be able to actually formally prove this. It's not about the technical details are important because the proof itself actually gives you all the most important intuition of how why sampling actually works. Okay? So right. So suppose that I have a solution path that has a certain level of clearance. And that means of all the points on the path, the nearest place to the obstacle is at least a distance rho from the nearest obstacle, right? So the idea is that I'm going to cover the solution path, right, with spheres of radius rho by 2. Okay, so you will cover the path with spheres, okay, and more. You will cover the entire path with spheres of radius rho by 2. And now if I'm going to generate random samples. Now, suppose the following happens. I have one sample in each of these spheres, one here or one here, okay? And then because of the way that these spheres are constructed, if I have one sample in each of those successive spheres, I will be able to connect them with a collision-free path. That's exactly because the way I have chosen the size of the spheres, because there's a bigger sphere that's collision-free out there, so I can connect these two successive samples by a collision-free path. All right? So I'm almost done here. Okay, so if I cover the path with all these spheres and put one point in each of the spheres, and each pair of samples can be connected by a collision-free path, that implies that I will be able to have a path that goes through these sampled points from the initial configuration to the goal configuration. Right? Now, the rest is just to calculate the probability. What's the probability by sampling a set of points uniformly randomly, and make sure that one sample falls in each of those spheres. Right? That can apply a union bound, and you can do the calculation very easily. And once we've done the calculation, it turns out the probability is pretty reasonable. Right? So this really shows us that the intuition behind the sampling-based algorithm, which is to cover the configuration space with spheres of certain suitable size. Right? In particular, you have to cover this solution path. Right? So I'm using random generated samples to cover the configuration space. Can I cover it using something else? Yes, you can. You can use a fixed resolution grid to cover the configuration space as well, right? The problem with that is that how do you choose the resolution? You will know in advance, right? So sampling allows us to cover the configuration space incrementally. And so the number of samples will adapt automatically to the underlying complexity of the problem until the path has been found. Now back to the issue of computational complexity or intractability. So does somehow the probabilistic sampling magically solve a computationally intractable problem? No, right? Impossible. Well, quite unlikely. So it does not solve the most difficult instance of that class, right? So if you have a high-dimensional space, and your solution must go through a very confined place, or in the worst case, a particular configuration, that is the needle in the hay space, in haystack, and in the worst case, you will have to cover the entire configuration space in order to find that place. And if that happens, that's the worst instance of that motion planning class. And if that happens, the computation will be exponential, and it will be intractable. But fortunately, oftentimes we are not in that most difficult instance, right? If you look at this space over here, our daily experience, we can go in and out, move from here and here, and our space has been constructed. If you think about it, that our daily living space has to be constructed to make our motion convenient, right? We did not construct. Even Status Center already has a very complex kind of connectivity, right? Still, that you can see that enough features to distinguish one place or the other that allows you to navigate relatively easily, right? Data center is not constructed to be a maze for you to do a exponentially difficult combinatorial search, right? So this is really the place where we reconcile the theoretical result with our daily experience. So what I usually say about those computationally intractable problems is that, well, I think it's okay. We do not solve the most difficult instance of that class. That cannot be avoided. But we should solve all the rest, right? So sampling is a powerful way to deal with those kind of problems. Now, we want to cover the space, right? So all that matters is where we put the samples. So let me give you a couple of examples of good samples and not so good samples. So on the left, look, this red thing, this is a configuration space with obstacles like this. And it is these places, these places that are kind of difficult. It's a small, narrow, right? So in the sampling-based motion planning, usually that's called narrow passages, right? So it's to go through here. If you want to go to this side to the other side, you can go through here. You can imagine that we extend the obstacle a little bit, make it further narrower and narrower. Yeah.
How do you decide which nodes to connect to the graph?
Right. So we can. A simplest way is to connect all pairs. All right. But we may, for computational efficiency reasons, we might decide that points far away are probably unlikely to be connected if it's lots of obstacles along the way where I will collide with something. Therefore, with the help of distance metric, we only connect pairs that are sufficiently close to each other in terms of the metric. Yeah. Now, well, this looks pretty good. And this even visually will tell you that this is less good, right? So all the samples fall in a corner of the configuration space because of a bias. And if somehow I want to figure out how to go from here to here, well, this roadmap is not going to tell me how to do that, right? So this samples is not very good in terms of coverage. Okay, how about look at this example then? Well, this looks that the samples falls relatively well all over the places, right? And except that well, there's no connectivity from the right-hand side to the left-hand side, right? So a good set of samples not only has to be good in terms of covering the free space, but also have to be well connected, right? It is these kind of places, which we call narrow passages, and that causes all the troubles for sampling. That kind of things, this I draw it in the configuration space, but this corresponds exactly that in those nail puzzles, in that place where that two pieces gets locked together, and you have to move in a specific fashion, this twisted fashion, in order to entangle them, right? Right. So I have, let me see. Okay. So the next thing is that, okay, sampling based motion planning is about where we put the samples. So that is controlled by the sampling strategy, right? That's for practical performance, that's a very important issue. And therefore, a lot of work has been devoted for this idea. If you look into the literature, there are lots of papers that tells you how you put the samples. I'm just listing some of the selected example here just for to give some illustrations. So there is this visibility-based sampling. So this is uniform sampling. If you have a space like this, the middle portion is the obstacles, you can generate a set of samples like this, right? So there are many samples here. But on the other hand, it's exactly equivalent to these two points, right, in terms of coverage. See, because both the chamber on the left and right are convex, so you can use one single sample to cover a chamber. That's just equally good. So we really don't need lots of samples over here. So in order for sample efficiency, right? So you would want to say that if it's already been covered, I don't want to generate more samples in those areas. Now, all the kind of things below is to deal with narrow passages. So there's a narrow passage over here, and then the narrow passage you may not see it very well, so they go through over here. So there are all sorts of ideas to say where we should put the samples. You want to bias a sample by using heuristics to reduce the number of samples in order to cover the space well. So this medial axis that says we should generate sample bias the samples to have higher density along the medial axis of the free space. And the Gaussian sampling is really saying that we want to have a high density near the obstacle boundaries, because in the narrow passages, the obstacle boundary are much closer to each other, right? So, and even other tricks to say that, well, boundaries is still too much. If you generate, there are two pieces of free space here. If you generate samples on the boundaries, you get something like this, right? But what you really need is to generate samples in these corners by testing for certain properties to say that, okay, so is my sample near in a narrow passage? A narrow passage means that I have a sample that's free in the middle, and on the two sides that they both collide with obstacles. That's what it means geometrically to be a narrow passage, right? So if you can satisfy this kind of property, then this is a sample that's very useful, right? So you can test for that using rejection sampling and so on and so forth. A variety of different kind of tricks. Yeah. No, it's automatically generated. That's right.
So just like the connecting problem, like if frequency always it doesn't connect, right? I can just add one more sample and package, right? Then it's gonna connect. So I think if we add humans, if that do something important,
Oh, okay. So yeah. So right. So let's say that the humans represent some kind of prior knowledge about what we understand about the underlying space. If we have such good understanding of that, definitely we could incorporate this kind of knowledge. In fact, in each of these examples, I'm incorporating human knowledge over here, right? So human analyze the problem, saying that I'm covering the space, and if you repeatedly covering that, that's not a good idea, so I don't want to do that, right? And then here it says that, oh, I mean, sampling at the boundary is a useful thing, right? I mean, if I want to squeeze through the door, and sampling on the boundary, generate more samples over there will help me to navigate in this way to squeeze through in certain places. And these are all the human knowledge that designer has been put in order to bias the sample in order to improve the efficiency of the algorithm, right? But I also want to point out that the human knowledge also has a limit on its reach. Now, the configuration space, the picture I have drawn for you, right? I mean, it looks kind of some kind of visual. But in reality, you know what it really looks like. It's an abstract space. The main difficulty of the configuration space is mathematically it is well defined, but computationally we cannot explicitly represent those configuration space obstacles, right? We do not know. In fact, we try to avoid explicitly computing those obstacles. If we actually try to do it, that exactly falls into the trap of computational intractability, right? So in fact, in order to prove the original proof of the computational intractability is exactly relies on the fact that you need to squeeze through some kind of a narrow place, and you have to construct the surface of the obstacle boundary in a certain way, and that makes it really very, very complicated, like a key in a hole, in a peg hole kind of setting. That makes it very, very difficult. Okay, so our intuition about configuration space has a limit somewhere. Okay. Yeah.
Moving back two slides, you have the C-spaces visualized between a good and bad sampling. I saw that there was two segregated groups. I was curious, is there a way to detect segregation of groups in a semi-efficient way and ensure that there's adequate connectivity between those?
Yeah. So I think there are two parts in which you're saying that one is to detect whether I have multiple connected components, and that we can maintain how many connected components together. Now, if we want to connect them together, right? So we don't actually know whether they're actually connected together or not, right? So we may have reason to suspect that if two connected components are very close to each other, for example, that we may add more samples over there. So by looking at the set of samples we already have, we can adapt the sampling distribution to sample in certain places more densely than others. So this is adaptive sampling that will improve the efficiency of the algorithm. Sure. Now, let me try to summarize a little bit here, over here. What we have got so far is that the configuration space is able to capture all the information for motion planning in a single unified representation, right? So that enables us to abstract away the details of the shapes of the robot, the kind of constraint it has on its motion, and just think about a path with suitable properties. Right? So it's a way to think about it. So the different way to think about it, if you prefer, you could think about it in the physical space, in the workspace, but that seems to be, depends on the detail of the robot, it's kind of difficult to capture, right? So the rounded and the rectangular. At one time, before the time of configuration space motion planning, indeed, that if you look into literature, there is a paper over there for triangular shaped robots, and there is a paper for a rod robot, right? And there's a paper for robot that translates. There's another paper for a robot that translates and rotates. You can write lots of papers that way, but the configuration space would be able to unify all of them and enable us to come up with a single algorithm to solve all the problems and understand the core difficulty of the problem, right? And now, as we understand the way we understand it, one of the core difficulty of motion planning is this high-dimensional configuration space, many degrees of freedom, right? And the sampling is a powerful idea for us to deal with high-dimensional spaces. And one of the crucial elements that affects the efficiency of a sampling-based algorithm is the sampling distribution, which determines where we put the points, right? Ultimately, all that matters is where you put the points, right? So let me take a pause here and see whether there's any questions on the main ideas here. How do we generate the configuration space? I mean, the configuration space versus configuration space samples? The space itself is by definition, right? So the configuration, it's an abstract mathematical definition that says the configuration space is a set of parameters that uniquely determines all the positions of all points on the object. And so as soon as I give a parameterization of the motion of the object, that determines the configuration space itself. Right? I gave specific examples like a disk that is, if I use the center point of position of a center point, right? Mm-hmm. Uh-huh. Oh, how do I construct it? You're saying, how do we construct the configuration space obstacles, right? So that can be done. Mathematically, that's well defined, right? It's a set of points that leads to the robot to collide with the obstacles. So mathematically well defined, no problem with that. Algorithmically, you can do that in some limited cases, in simple cases. For example, for polygons in 2D translates only, you can compute the Minkowski sum to do that, right? And if it's three-dimensional, it translates and rotates, so it's a three-dimensional configuration space. You can stack it together. So you compute the Minkowski sum for each of the orientation and stack all of them together. So these are the limited cases. In general, so I want to emphasize this once more. The reason that we use sampling for configuration space motion planning because we do not want to explicitly construct the configuration space obstacles. Conceptually, it's very useful to think that way. Algorithmically, we do not want to do that. Yeah. We'll get to that, your point towards the end. Yeah.
So can you explain the practical differences in how you approach the problem in a very high-dimensional space? For example, the robot you were showing earlier with the 30 degrees of freedom, or 30 legs plus however many degrees of freedom, and how you approach that differently than a much smaller robot.
Yeah, so the key difficulty is that one of the key difficulties, if you think about a space with so for a 6, 7, I mean, our intuition all gets a little bit messed up when the dimension exceeds. I mean, because our intuition is based on a three-dimensional world. We can sort of extrapolate a little bit to the six-dimensional space. By the time it gets 100, I mean, lots of things are wrong, right? In a 100-dimensional space, every point is far away from every other point. If you take a neighborhood, there are no neighbors in it, right? So it doesn't matter how, in a 100-dimensional space, doesn't matter how many, I mean, given a reasonable amount of computation time, and doesn't matter how many samples that we throw in, they are mostly just sparse, very sparse. So we must focus the samples on a lower dimensional space, and then we will have to figuring out based on our past knowledge what this non-dimensional space is. Now, in order to do the one that the 35 degrees of freedom robot to do that, we in fact that use the workspace knowledge in order to guide the sampling process. So you want to say things like, I want to sample more densely in the obstacle boundary, things like that. But that itself is not sufficient because obstacle boundary, if the configuration space is n-dimensional, the boundary is n-1. That doesn't help a whole lot. You need a lot more powerful things in order to focus the sample on the places that are important. Yeah.
So just now I saw that you use abstract, and you saw you use other algorithm. But usually compare with the classifier the A star, if we have a reasonable heuristic, A star always outperform the depth.
Yeah, so I'm not getting to the optimality yet. I'll get to your point a bit later when we talk about optimality, right? So in the interest of time, let me try to move on a little bit, okay? So now we have talked about all the key ideas for sampling-based motion planning. The next thing we want to do is to make it actually kind of really work in practice, right? So the schema I present to you is something like this. Let me first sample a set of configurations and construct a roadmap. Construct the roadmap first, and then I do a search, right? Now, one question we can ask, is it necessary to construct a roadmap fully just to search for a single path? The answer is no, right? So look at this. We have multiply connected components. If I just want to search for a single path, surely I don't need to, let's say that a path is here. I don't need to construct the rest of the things, right? So the idea then is to improve computational efficiency. What we want to do is to interleave sampling and search. So instead of go through a two-stage process, construct a full roadmap by sampling and then search, we want to interleave these two steps and iterate on that, right? So a little bit more specifically, what we can do is to grow two trees rooted at the start and the goal configuration. So we want to find a path between start and goal. I'm going to build two trees that start from the one rooted at the start and the other ones at the goal. And then we'll extend a tree by iteratively choose a node from a tree and sample in a neighborhood, right? And suppose we have two trees, and then we'll try to connect these two trees together, right? Now, because it's a tree, like each leaf node in the tree has a path that goes all the way to the root, right? So if we are able to connect these two trees together, so that means that we can trace these two paths to go from initial to the goal, right? So that connects the sampling and the search automatically together in an iterative fashion. So let me give two specific examples of this idea. The first one is called the expansive-space tree. The idea is to sample, when I extend the tree, I want to sample low-density regions, the place that are not well sampled. Right? So intuitively, it makes sense. That's what we want to do. Now, so to do that, we need to define the density. So suppose that I associate for each of the tree node a weight. So the weight of a tree is number of other nodes. The number of nodes in a neighborhood is centered at that tree node, right? So it could be a sphere with a fixed distance. So in this example I'm drawing here, this neighborhood contains four nodes over here. And there's a different node here, and in the neighborhood it contains two nodes, so its weight is 2. And I want to choose the neighborhood for sampling inverse proportional to its weight. So the higher weight means a lot of samples over there. I don't want to add more samples over there anymore. So I want to sample over here. So I sample one more point configuration over here, and we check against the tree node if there's a collision-free path, and then we just add that node to the tree and insert an edge between this newly sampled node and its parent. Okay. So one thing I want to observe over here is that in order to define a neighborhood or a sphere, right, so I need a distance, and that is a distance metric that I need to define. So that distance metric will define the shape of the metric and ultimately define the sampling distribution, right? So where we put the samples actually depends on this definition of the metric. Similarly, this is a pseudocode. Again, you can see some of the details, but again, the key primitive here are these two. Can I determine our sampled configurations is configuration free and whether I can connect two configurations together, a newly sampled node to its parent. Okay? And we keep on extending these two trees, and then we want to try to connect it together. If it works, then we find the path. Okay? Now, here's one question here. On the right, I'm showing two set of samples. So this red part, again, are obstacles, and these are two sets of samples, each of them coming out from by extending a tree. Okay? So what I'm trying to ask here is that why do we need to use weighted sampling? Okay? What's the benefit of that? What if we just do it without weighting? Okay? So one question I want to ask is that if you stare at these two sets of samples, can you see visually the difference between them? So what's the difference? So yeah, this one has kind of forms a cluster and then more concentrated in the middle portion, right? So okay, I would say so the task here that your starting configuration is in the middle here, and the goal configuration is over here. Okay. Now, the other question I want to ask is which set of samples do you think is generated by the weighted sampling? This is slightly tricky. You have to, this first one? Okay, so I know this is slightly tricky. You have to think a little bit about if I generate successive samples, how the weights change, and where would I put the next sample? And that will give you the clue about what happens if I don't apply weighting. Which one is weighted? This one's weighted? Do you think this one's weighted? Right, the second one, right? So think of this way, that if I don't weight them, right? So if I add some samples, let's say in the neighborhood of the root, right? So there are more samples, and elsewhere has fewer samples. If I don't apply weighting, then more likely I'm going to sample over there, right? That's why this clustering becomes like this, right? So if we keep on doing this, that generates this unsuitable kind of bias that we don't like. All the samples focus on in the middle, and the rest of places, like important places like this, will not be sufficiently covered, right? And this set of samples, exactly by applying the weighting, the sample spreads out and covers the space much better, right? Yeah, so that's the thing here. So this is, of course, not the only way of doing this, and that brings us to the rapidly exploring random tree, which is widely used in practice these days. So it's actually very, very similar. It extends the tree in a slightly different manner. So I have a tree over here. So in RT, it says that, okay, so I'm just going to arbitrarily generate a point, a target point from some desirable distribution. Let's say I want to uniformly cover the space, so the target distribution is uniform. So I'll generate a target point from a uniform distribution over here. Then I'm going to try to find the node in the tree that's closest to this target point, okay? And I'm trying to then move towards that point by generating one more tree node in that direction, right? So you are trying to add more and more points towards samples that are generated from the target distribution. Intuitively, you can just think that my tree nodes will distribute kind of like the target distribution, okay? And now, again, I want to add here that there are a few places where we depend on the distance metric on the configuration space. Now, if I want to generate a uniform distribution, the distribution and the definition of distribution itself depends on the metric on the space, right? Furthermore, I want to look for the tree node that's closest to the target point, right? That again, the metric decides all these algorithmic details and ultimately determines the sampling distribution. There are variants for extending the tree. Instead of extending one step, you can extend more tree points, and these are some of the things that you can do in order to improve the computation efficiency and algorithm. So once I have two trees, again, that we are going to connect these two trees together by extend them towards each other. So now, by doing this sort of set of things, you can see that this is kind of the motion planning tasks that we can solve. Okay, it's moving to insert this big robot end effector into this car body, right? And also, one more example, that this has very weird object that you want to kind of extract from an assembly, okay, without collision. Well, I think the motion is a little bit delicate, and it'll be shown it from another view. And you can see that you actually have to have this leg insert over here and rotate a little bit in order to extract fully from the rest of the assembly without collision, right? So this is in fact the data set from the GM, and what it shows is that it's some kind of wire harness underneath the hood of the car, which is very closely packed, and you want to extract a part, take it out. When you design the car assembly, you want to make sure that there is a path that can extract it, to extract the part for maintenance purposes, right? So this motion planning examples is actually 20 years old now by now. So it's by today's standard, it will be on very slow computers. But the idea of sampling is powerful enough that even in those days, you were able to solve complex motion problems like this. Okay. Now, so far, we treat it as if that the objects move in kind of free form. You can move any way you like without any constraint on them. Of course, in practice, that's not always true. In particular, we have to kind of constraints on the motion we would want to have. So one kind of constraints is holonomic constraints. For example, I want my robot end effector in contact with a surface, right? In order to wipe the board, the end effector must in contact with the whiteboard surface, right? So, and this is called the holonomic constraints. So it's a constraint on the configuration of the robot. It must be in contact with some surface, right? And also that it could be inequality constraints that I do not want to penetrate the obstacles, right? So it's an inequality. But there's more than that. It's not always just as simple as a constraint on the configuration space. There are times that it's a constraint on the configuration and the configuration velocity. So it could either be equality or inequality. Furthermore, if we set the state to be a pair of a configuration and configuration velocity and iterate this thing once more, it becomes a relationship between the configuration velocity, and the configuration acceleration, right? And using that, we will be able to define dynamics because now we have acceleration built in over there, right? So some concrete examples. The most famous one, a car cannot move sidewise, right? So in pictures, that's what it means, right? A car cannot move sidewise because of the wheels. And so what do we need to do if we need to make the car move sidewise? Well, this is what we have to do, right? If you have a car and you live in Boston, that's how you do it. And I'm a terrible California driver, so I try to avoid that. Now, in formula, you can write it down, these constraints like this. So the configuration, so it's a car, it's a rigid body, rotates, translates in 2D space, right? So it's x, y, theta. Now, the constraint that the car cannot move sideways simply says that the instantaneous velocity of the car must be pointed in the direction of the orientation of the vehicle itself, right? So the theta is the orientation, tangent theta is a ratio of y dot over the x dot, or you can rewrite it in slightly different form in this. So it's fairly clear. It's a relationship between configuration and configuration velocity, okay? Now, one of the difficulty of this kind of equality constraints is it makes sampling much more difficult, right? So if it has no constraint, I can generate a sequence of random numbers represent a configuration, and I toss it into the configuration space and check for collision, I'm done. Now, if I try to repeat the same thing, and when I have a constraint, I toss one, well, it may not satisfy these constraints. I can toss a lot of them, And none of them would satisfy. The reason is that the inequality constraints defines a lower dimensional manifold in the configuration space. The measure of that lower dimensional manifold is 0, so the probability of sampling on the constrained surface is exactly 0. So I can toss a lot of them and get none free configurations, right? So that's bad. What we need to do is to come up a different kind of representation of the constraint. So again, this is the usual way we would write the constraints for for a car. And what we are going to do is to reparameterize this in the following form. Okay, so we have done this. Now, the details aside, what you can check is that if you plug in these things into this constraint, the equality is satisfied. Roughly what it says is that I can control, the v is actually the speed, right? So the phi here is the steering angle. So if you rewrite the constraints in this fashion, there are certain good things that's going to happen, right? So more generally, suppose I have a configuration like this, and I have a constraint on the configuration and configuration velocity. We can try to reparameterize this constraint and write it in this form. So roughly speaking, I'm solving for this inequality, and I'm writing the configuration space velocity as a function of the configuration and some free parameters, u. And u normally it's a control, and so it's a controlled dynamic system. Okay. Now, once we represent the constraints this way, and sampling again becomes very simple. Okay. Now, suppose we want to extend a tree and by generating a new sample. What I can do is instead of sample directly in the configuration space or the state space, we can sample a control. Right? We can sample control, like in the case of car, we can sample the speed and the steering angle. And then I can integrate this dynamic system for one step forward for a duration of delta t. And the rest doesn't change. Right? So the algorithm. So again, we can generate new samples, and everything is good now. So this is one way. This is one way to deal with constraints and sampling in a constraint space. It's called the reparameterization of the constraints. There are other ways to deal with constraints. I'm going to illustrate with some of the pictures here. One is to relax. Okay, so I mentioned one of the difficulty with constraint is it generates zero measure lower dimensional surface, right? So you can relax a little bit to epsilon, and that may help for certain kind of problems. The other idea is to project. Okay, so I generated a sample that violates constraints, but I can project it down to the constraint surface, right? That gives me a sample. And yet another way is that suppose I already have a sample on the constraint surface, and locally I can linearize the system and generate a tangent space. A tangent space, I can move on the tangent space locally and generate samples in local neighborhood, but that only gives me a small neighborhood of it, and then there's another idea that's related to the tangent space, but in a more global manner. So you actually we generate these atlas, what they call atlas. Basically, it's a decomposition of the constraint surface into pieces. Each piece can be reparameterized linearly or in some other simple form. Okay, so this gives you a bunch of general ideas how to deal with constraints. So far, all we have talked about is admissible motion that satisfies all the constraints, right? So if all we do is that, and you actually try to implement the algorithm and run it, and say, well, start from this is the initial configuration, and this is the goal configuration, and generate the motion. And you run the sampling-based motion planning algorithm, very likely you go something like this, okay? And this is probably not what you want. You want this. Right? So what we need is some notion of optimality. Okay? So we want not only valid motion that satisfy all the constraints, we want them to be optimal according to a certain objective function. So, okay, so you can define objective function in whatever way you like, but the one idea to do it at one time suggested to me is the following. Okay, we have the RT algorithm. Some of you may have heard about it, and even if you have not, we said that it seems that generating more samples is kind of a good thing, right? So one way, if we want an optimal solution, this is one way to do it, right? run RT for a sufficiently long time and generate lots of samples and choose the shortest path in the tree. Okay, and do you think that that works? Why? Okay. 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 So in simulation. Okay, let's just forget about the hold on a second, let me finish this thing, I'll get to you. I know you're interested in optimality. Let's just forget about the details of the imperfect models of real world and stuff like that. Let's just think about simulation, all right? All sorts of robots in simulation. I'm just going to generate enough samples using RT algorithms, and once I generate enough samples, then I find the shortest path in the tree, right? Would that give me shortest path, at least if I generate enough samples? Yeah, I'm gonna take this one. Anytime RT, okay. Yeah, in what sense? It might work, you think?
No, I think RT we generate the path, and for example, in 10 seconds we can generate the path and update path.
Yeah, update, and the next path will be better than the previous one, and we can keep on going, and we might get up with the shortest path, right? The best path we can have. Yeah, this is the intuition here. But any other views? But I'm on all the path, right? I mean, but I can connect it. So there are two trees. I can connect many pairs, and there are different ways to connect it. So that makes it multiple paths. Yes, yeah. Once you connect two trees together, it becomes more like a graph. Yeah. Limited graph.
I believe if you did that for a low dimensionality problem, it should work. I think for high dimensionality, it may not be effective. I guess it's.
Okay.
I'm just giving you a opinion.
Sure. No, I mean, it's very tempting. It's very tempting. Now you know what the answer is, right? So it's very tempting. So it's you can do optimization, but you can do formal optimization. Yesterday, Brian mentioned that there are different ways to formulate problems and using optimization techniques. And optimization, if you use a gradient-based techniques, usually gets you stuck in the local minimum, right? So, and the problem we deal with can be highly nonlinear because of the different obstacles that cuts the path into different non-homotopic classes, right? So you cannot continuously morph one into the other because of the obstacle sits in between, okay? All right, so it is tempting. Actually, a lot of people think that would actually work, but unfortunately, that is wrong by a long stretch, okay? So I'm running down the proof over here, but we'll skip over there, and I'm just going to show you the picture, and if you just see the picture, you know something is badly not quite right here. Okay, so this is the RT algorithm, and the problem is very, very simple. I have an empty space over here, okay? And the starting point in the middle and end point is here in this purple square inside. And I want to find the shortest path, go there. And we already know the answer, it's empty space, so you go directly over there, right? Okay. And this is the kind of tree, if you keep on extending the tree, this is what the RT will give you, it looks like. This is an improved version called RT star, which I'm going to tell you about in a bit, but regardless of the details, well, if you look at this tree, the shape, the path that's encoded in this tree, you will imagine that this one probably will get you the shortest path. And this one, there is no way, right? So something is badly wrong over here, okay? So what is badly wrong, okay? So let me show you what's badly wrong, okay? So this is the RT algorithm that I showed you, how it extends the tree by adding one more node. Right, so this is the target point. I say, well, this tree node is closest when I extend by this new node, and if this new node is collision-free and it connects to the parent node by a collision-free path, I add it to the tree, and I'm done. Okay. Now, suppose you are looking for a shortest path. Well, have you thought about what if there's a different way to connect this to this new node. In fact, this node also connects to this tree node. Plus, that if you consider this path and this alternative path, the cost of B is actually shorter than the cost of A. Now I have kept this path in the tree. Now I will be badly wrong. Okay, that's how it messed up. Now this sounds maybe a little bit. I mean, so in the literature that well, in the RT algorithm, so the RT algorithm, RT star algorithm, in order to fix this, it's exactly what it's doing. It's called a rewiring. Okay, and that's exactly the step that you compare the cost of alternative path and try to reconnect properly. Okay, so this may make you feel a little bit mysterious that, okay, so we need to do this, what else I need to do, and so on and so forth. Am I going to actually get optimality? Of course, you can go through the proof and understand that actually by doing this, that it is exactly the rewiring step that generates the correct optimal path. Okay, but in fact, without going through the proof, and that's actually a very simple way to understand this actually, which is to compare with the Dijkstra's algorithm. Okay, so that's why I showed you the Dijkstra's algorithm. Anyway, so in the Dijkstra's algorithm, there's exactly a step over there to compare the alternative path, right? So if you look at the details, if you recall the details, alternative, the Dijkstra's algorithm, there's a step called relaxation, which basically is to connect alternatives, compare alternatives, and wire it along the shortest path. So that's exactly the same. So one very simple way to understand sampling based on motion planning is to think of it as a search problem in continuous space. Therefore, we need to discretize the continuous space by sampling and the search at the same time. So you interleave the discretization by sampling and the search problem. So everything we normally would do in search, we still have to do, even if we sample in a continuous space. Anything missing, that will lead to the wrong result. Okay? So now, of course, that we can put all these things together, right? So if we compare the RT star with Dijkstra's algorithm, right? And again, that we know that we can improve the computational efficiency of Dijkstra's algorithm by adding an admissible heuristic, like A star algorithm, right? So we can do the same thing here. Okay, so we can add a heuristic to the search, and that leads to the bit star algorithm. Okay, and also that we maybe want to have optimality and the constraints, and they can be put together as well. And this is the SST algorithm. Right? All right, so we are. Let's move on. Now comes to the most challenging and exciting part. I mean, yesterday this word uncertainty gets mentioned in multiple ways, multiple times already, right? So uncertainty. So uncertainty can be understood in various ways. You can think of that as intervals or sets that bounds the possible states, right? You can also think of it as a probability distribution over states. Is that all fine? So I'm going to give you a pictorial representation of uncertainty in terms of a tree search. Okay. So first, action uncertainty, basically imperfect robot control. Right? So if I apply an action, so each of the tree node here represents a particular state, right? So that's a dot within this tree node represents. Now, if I have a deterministic system, so after I apply an action, I'm supposed to have a single follow-up state. Because of uncertainty, because of uncontrollable factors, I may end up with different states. That's beyond my control. So in essence, now I get more branches in my tree. Right? Now, then there is observation uncertainty, or you can call that sensor noise. That makes things even worse. Right? Because of sensor noise, I'm no longer be sure which state I'm in. Well, the sensor doesn't tell me exactly which state I'm in. So I have a probability distribution over the states, and I'm kind of illustrate here using three sampled states and draw it over here within a tree node. So in general, it should be a probability distribution over the states. Now, if I apply an action, right, And because of sensor noise, and I may end up with different observations. That's again, that I cannot control that part. So it's again, you can think of that as a tree search, but it's a tree search in a different kind of space, right? Each tree node here, so here each tree node still represents a state. Here, each tree node represents a probability distribution over states, and usually we call it a belief. Right? A belief is a probability distribution of the states. Nevertheless, we still can solve our search problem in the belief space. So this is my search tree, belief search tree. So each node in the belief search tree represents a belief, which is a probability distribution over the state space. Okay? And at each of the tree node, I branch on all the actions available to me. And after I take a particular action, I may get different observations, so the tree further branches. Okay? And now if you look at any particular pair of action and observation, so I have an initial belief, I apply some action and receive an observation over here, and I can update my belief using a Bayesian filter. Remember, yesterday we talked about, Lucas talked about Bayesian filter, right? So I have a distribution, I update it with an action and then an observation, right? So we can filter it. So except that yesterday it's about a state estimation problem. So I'm given the action and the observation, right? So that leads to a filtering problem, but today I'm solving a control problem. I'm just trying to choose between the different actions I can perform, right? So that's why the tree starts to branch. Yesterday it doesn't branch because the action is given and observation is also given, right? So I have to reason about all these tree paths, and obviously the tree path. So we have lots of actions, lots of observations because of uncertainty, and the tree can grow very fast. But conceptually, this is not that bad at all, right? So if I want to solve this optimization problem, I can apply the Bellman's principle of optimality, which says that if I want to find the best action of the root at the root, what I can do is to choose the action that maximizes the sum of two terms, and one is the immediate reward. I mean, just think about the task as maximize some kind of reward object function. I mean, you can think of a shortest path as well, except that in the case here, usually we think of reward, which is the negative of the cost. Okay? So you maximize the sum of two terms, one is immediate reward, and the other term is the expected future reward. Okay? I need to take an expectation over here, because I do not know, after a given action, what future observations I may receive, right? That's returned to me by the sensor. I cannot control that part. So I have to take expectation or average over all possible observation I might receive, right? So I just recursively apply the Bellman's equation for optimality and search the tree and choose the action that gives me the highest reward. So again, it's a tree search problem, right? Except the problem that is that the search tree lives in a belief space, the space of all probability distributions that can be enormous. All right, so let me give you an intuition of how bad that space is. Right, so this is our usual state space or configuration space. Earlier we talked about the high-dimensional configuration space. Right, so we said that the difficulty is that if I have 6-dimensional, 6 degrees of freedom robot, I end up with a 6-dimensional configuration space, right? So if I have discretize each of the dimension by 10 values, it's 10 to the power of 6. Now, because of uncertainty, I don't even know which state I'm exactly in, right? So I can be in any of these states, which is color-coded over here. Now, suppose I represented the distribution in a discrete manner as a vector, and each entry in the vector represents the probability of the robot in that particular state, right? So then I'm going to be in the space of this kind of vectors. Now, if you think about this, right, the number of entries in the vector is exactly the number of states we have. That's already exponential in the number of the dimension of the configuration space, and plus I'm in this vector space of the number of entries over here. Right, so which means that the dimension of the belief space is doubly exponential in the number of degrees of freedom of a robot, right? No computation will survive doubly exponential growth, right? Forget about this. So the saving grace is still sampling, except that we have to be much more clever in terms of how we define a sample, right? So this is the general idea here. I'm going to rely on a very general idea of thinking about uncertainty. Now, when we think about uncertainty, you just think about in terms of future scenarios, right? So uncertainty simply means the future things that I don't know about. And it becomes very hard because there are myriads of future possibilities that I cannot enumerate all of them, right? But what if I can, right? So one way is to think of uncertainty as a sequence of random numbers, and that determinizes the outcomes of future events. So specifically, so we can simulate an action sequence and determinize the outcome of simulation by a sequence of random numbers. Okay, this is how I'm going to do it. Now, just keep in mind that it's uncertainty, right? So the action's consequence is non-deterministic, right? And the observation is, again, non-deterministic, but I've claimed that I'm going to determinize all of them just using a single sequence of random numbers. This is how I'm going to do it, okay? So this is my random sequence, okay? And to simulate that sequence, the sequence of actions, what I'm going to do is to use the first random number to sample from the initial state distribution and pick up a state using that first random number, okay? And then I apply an action, and I can propagate the system forward and generate a new state. Again, because of the imperfect robot control, I end up with all different kind of future next state. Again, I'm going to use the next random number to pick one of them, okay? And now I'm going to receive an observation. Just remember my tree branches on all the different observations. I'm going to use the row 2, the next number in the random sequence, to choose one of them, okay? And so on and so forth, which means that the sequence of states, action, and observations are entirely determinized or chosen by the sequence of random numbers. Given a sequence of random numbers, and the simulation trajectory is entirely fixed. Yes? Chooses the initial state from the initial state distribution, and then when I propagate system forward by applying A1 to S0, that is, in principle, that will lead to many possible follow-up states, right? And then I'm going to choose one using the next random number, row 1.
So the state distribution changes when you apply A1 and then use row 1 to choose from that next.
That's right. Yeah.
Okay.
Choose a particular state from the next the propagated distribution. Okay. Yeah. So, and I can associate this simulation trajectory with a sequence, a path in the tree, which is a particular sequence of action and observations. Right. So this is that's what I mean by a scenario, and how I use a sequence of random number to determinize away all the uncertainty. Okay, and I can repeat this trick using a different random sequence, and in total for k different scenarios, and I can do this for all the action sequences, right? I can repeat all of them. Now I can, yeah.
So sorry, just to go back a little bit, does our choice of S1 then depend on what S0 was?
Yes.
Okay, so
yeah.
S0 is
I'm just performing, just think of that as simulation, except that the outcome is chosen by the random numbers that I have fixed in advance. Okay, right? So in general, when you perform a simulation, you have to rely on a random number generator, right? So instead of using a random number generator, I will generate all the random numbers in advance for you. You just look at that sequence of numbers and choose the next state and next observation. Okay. Now, instead of applying this to a fixed sequence of actions, I can apply it to a tree as well, right? So this is my original tree, which I claim to be way too big. And so using a fixed sequence of random numbers, I can actually choose some branches of the tree and sparsify the tree greatly, okay? So this is a subtree that determines, chosen by this sequence of random numbers. What you can see here is that any path over here, which is a path from action, observation, right? So this basically corresponds to a simulation path that's determined by a particular sequence of actions, which I talked about earlier, except that this is a tree because I have to consider all the action branches. Right? So it's the same idea, but applying to a tree. So every path here corresponds to a tree path. All right. So now further, that the different paths here are correlated because they're all chosen by the same sequence of random numbers. But no worry, that does not affect the guarantee, the theoretical guarantee of the optimality of the result. Okay. So the most important thing is that this tree, right, contains all the action branches, but after each of the action contains only one observation branch chosen by the random number, right? So this tree is greatly specified because the observation branching has been reduced to only one of the many possible ones, right? But this is for a particular scenario with a particular sequence of random numbers, and I can do this k times using k different sequences of random numbers. And I'm going to put all these trees and collapse all of them together into a single tree. That's what I call the determinized sparse partially observable tree. The name is slightly awkward, just so that we can make up this acronym, DESPOT. Now, this is the idea of tree search for planning under uncertainty, right? So all we need to do here is generate some sequences of random numbers and construct this tree, right? And search this tree. And again, that even though in a very large space, that is still very easy to straightforward to do. And now, if you look at the size of a tree, original tree is exponential in horizon and with respect to the number of observations. If you use very rich sensors like visual cameras, the number of observations is the number of different images that you can have, right, which is an enormous number. And using sampling, you can reduce to a factor of k different scenarios. And there's a theoretical analysis that tells you that how big a k is, and k does not have to be too big under suitable conditions. I won't get into details, but the most interesting thing is the theoretical result basically says that if your problem that admits a simple solution, simple in the sense that your optimal solution admits a compact representation, then this will work and work well, and k can be very small, and that'll be fine. All right. So what does it mean that an optimal solution admits? For 5 slides, and it'll be done. Yeah. So the simple means that the compact representation means that if you represented the solution optimal policy as a finite state automata, there'll be a small number of states. If you represent it as a policy tree, you have a small number of tree nodes. Okay. So let me quickly say that it provides guaranteed performance, and it actually works well in practice. It can achieve real-time performance in online planning, in autonomous driving, and also that I mentioned that it's actually fairly simple to implement. It doesn't do too much. You don't need to do too much. You just need to sample random sequences, construct a tree, and do your vanilla tree search, right? So this is what you can get. This is the video that I showed you earlier at the beginning. Let me run the full length of it. It enable the vehicle to navigate among pedestrians under uncertainty. And even if we do not, the main uncertainty here is that we do not know the intention of which way that pedestrian is going to walk. Okay. And in order to make the system robust, we replan at the 3 hertz at each step and plan multiple steps ahead and execute the first step and then replan. Okay? And you can see that the system is reliable enough that we can actually put children on the vehicles. And and that's what their parents would do if you put children on the vehicles, right? Jump right in front of the vehicle, and hopefully the vehicle will still respond in the right way. Okay. And let me summarize here. So motion planning can be treated as, really I want to tell you that one message that you want to keep in mind, the motion planning can be treated as a search problem in a continuous space. And interleaving sampling and the search improve the performance. And we have a lot of interesting issues here: constraints, optimality, and uncertainty. and they can all be treated in a sampling-based framework. Okay? Let me briefly tell you some of the tools that are available for doing motion planning. There is this open motion planning library, and that covers many of the algorithms, state-of-the-art algorithms that we talked about, mentioned here, and more. And it's well documented and well supported. And if you want to use ROS, I mean, it's supported as well. And unfortunately, it doesn't address the issue of uncertainty. And now for that, you can use our software. It's not as well documented, but for many people who have used it, and the code is fairly reasonable, and you can try it. Okay? Let me end by with this famous kitchen example, right? We talked about a lot of things. Are we done? Unfortunately, not quite yet. So, okay, this is the famous kitchen example, and in the future, we may want to tell your kitchen assistant robot or your butler robot pass me that frying pan, please. Okay, so and here is go. And now, before you can do anything about planning, you actually need to figure out where. I mean, your perception module actually to figure out where the frying pan is, right? So how can we the robot act in such a way that improves the perception and detect and recognize the frying pan easily, right? And furthermore, that in order to plan, we need to have a model of the environment. I mean, where does that model come from? I mean, here, right now, I just assume that someone has given to me. So how do we get that model? If you want to try to, we can try to learn a model, but try to learn a suitable model in this mess, it will be very, very challenging, right? So how can we connect planning and learning and perception all together and overcome the challenge for motion planning in terms of geometry, dynamics, and uncertainty? Thank you.
Okay, so we're going to have a 15-minute break. If you have additional questions for David, then please come up.